So the big idea here is that what we really want to do is this item here, which is that we want to actually find um, the longest consecutive items. So obviously this 4 is the longest sequence, so that we have our answer is this one, but we need to translate it into a computational way of calculating. That's why we bring in um, these items here to allow us to actually be able to use a computational method to actually get one. I mean, 2 is like the computational way of like doing things, right? So the third thing to actually mention is that there's a way to actually to visualize things better, which is by drawing like a sort of like a timeline thing. So obviously when you see like the 3, it's very easy to say that which one has the longest sequence. Obviously this one is a sort of like a longest snake per se. And now it's very hard for us to actually derive out from nothing into coming to become the number 2, right? And I'll argue that this number 3 is called out like a Z is because it's just like an imaginary thing. What's the real challenge is that transforming from the 1 to the number 2 is a big jump. And in between the big jump, I think what we can actually do first and foremost is by visualizing through the Z diagram, and actually through it, the Z diagram, we can actually try to actually form some sort of like logic into it to actually make ourselves student in from the transition from stage 1 to stage 2. So that's why in Z we started off like doing like some sort of logic items to actually do. So first, maybe say for let's play out. We have 100, and then we can before it we actually see the diagram Z, which is say that how do we know anything that is of like a starting sequence? If you were to see that starting sequence is that they don't have a left neighbor. And if there's a sequence, that means there's a right neighbor. But if there's no continuation to the starting sequence, there will not be a right neighbor. So we're gonna use that to play with our playbook. So first thing first, right now we're gonna term this as stage A per se, and this is our sort of like a stage B. where we start doing our records over here. So stage A, so we go through the raw input and maybe say call this a C diagram. C diagram is our raw inputs. So we insert the 100, put in the 100. We first check if this is a starting sequence by checking if there's a left neighbor or not. So we check the left neighbor, there isn't any value. So we acknowledge that actually this 100 will then become our starting sequence. So you then argue that how do I actually go about to actually establish it that way. So say for example a number like this, 100. One common pattern is that it doesn't have a left neighbor. So you compare it to maybe say we use the same example, 4. So is this a starting sequence? We first check, is there a left neighbor? There is actually a left neighbor, which is 3. So therefore this one is not a starting sequence, but for stage 1 this is a starting sequence because it doesn't have a left neighbor. So if you want to argue that how to know there's this thing is not a neighbor or not, we can check with stage 2. Stage 2 check with the left neighbor, there's a left neighbor, therefore this is not a starting sequence, which we can see over here, right? If you check the left neighbor, there's a number, this is therefore not a starting sequence. So we jump back to Z diagram, we start inserting more numbers to it. So this is not the left neighbor, there's no left neighbor, this is a starting sequence. And every time we know there's a starting sequence, we jump to diagram B and start registering into our records. We record it in that 100 is like a starting sequence. I don't know how we do it, but and before anything else, we do establish everything as being sort of a set. The reason why is that, say I got 200 over here, I'm gonna keep on like checking, maybe say this is a 200. I'm gonna rinse and repeat something that is like, I'm gonna check everything with the same thing. I'm gonna loop three times of an operation that is carrying out the same operation, which is not what we want to do. So I visualize it as this way. So say I have 100, a 4, and a 200, and then a 200. So this is obviously not a set, right? So maybe say my 200 is supposed to act like an operation towards this 4. And then if this thing is not a set, which is stage 1, stage 2, right? So stage 2, obviously if my 200 is doing an operation to 100 and a 4, let's just say, for example, so to speak, then stage 1, if there's a duplicate, it will carry out operation towards the 4 again. So to me, this thing is a duplicate. that you don't really need to do. But for this one, there's no duplicate, so you only carry out once. I'm just saying that if there's a duplicate which can be displayed, can be played out at stage 1. Stage 2 is saying that if it's being transformed to a set, so you don't do unnecessary movement that which stage 1 is doing, which is, you can see over here, this 200 is doing a duplicate movement from previous, and it's an unnecessary movement per se. So therefore, it's necessary that we turn our raw input, our stage C, into a set, because we don't want to end up having this stage 1 redoing of items per se. So I mean, for stage B is that we just simply store the starting sequence value, which is the 100, which is by checking before left neighbor, no left neighbor, okay, starting sequence. And then the next step is that we check the right neighbor. Is there a right neighbor? So there isn't, so that's the end of this starting sequence. Now we move on to the second value, which is a 4. Same thing, we always check like if there's like a left neighbor or not. So there is a left neighbor, so this thing is not a starting sequence. And then we turn into checking the right neighbor. Is there a right neighbor to see? We actually don't do that. We just check until here, then we're done. Go to 200. Is there a left neighbor or not? No left neighbor, therefore it's like a starting sequence. Then we register it into stage B. Then we check if there's a right neighbor, since it's a starting sequence. No right neighbor, therefore end of sequence. And we end off stage B, 200, leaving it there. Go to 1. Is there a left neighbor? There isn't any left neighbor, so register him as the starting sequence. And then we check for the right side. Is there a right neighbor for this 1? Is there a 2 in the array? There is a 2. So it's a 2. And then we check, is there a 3? There's a 3. So we expand it even more. And then we check if there's a right neighbor for 3. Is there like a right neighbor of 4? There is a right neighbor of 4, so we register also over here 4. And then is there like a right neighbor of 4, which is a 5? There isn't any, so we're just gonna end not with like the 4 over here. And at the end of the everything, at the end of the day, we calculate the length of like each string. So this one obviously tell us that this is 1, this is 1, and this is 4. So therefore, this one will be our so-called longest consecutive. So yeah, there you have it. Everything comes to an end.